mathematicians. I am Annalakshmi from V.H.N.S.N.College, Virudhunagar. Now we discuss the theorem. If G is a finite group, then CA equals order of G divided by order of N of A. In other words, the number of elements conjugate to A in G is the index of the normalizer of A in G. Very interesting theorem. In other words, we use index of the normalizer. Why we use that word? First, order of G by order of N of A, that equals index of the normalizer of A in G. That is, order of N of A equals number of normalizer of A in G. By using Lagrange's theorem, order of H equals M, GH equals R, that equals left cosets. The left cosets are the index of the normalizer. So, R equals N by M, order of G by order of H. That subgroup is order of N of A. So, we use the word number of normalizer, that is index of the normalizer. Okay, now we see the proof. For A belongs to G, C of A, that means by definition, the set of elements X belongs to G such that A relation to X equals X belongs to G such that X equals Y inverse A Y, Y belongs to G, conjugate, okay. That equals Y inverse A Y such that Y belongs to G. That equals order of C of A, that is number of elements in G which are conjugate to A. Okay, order of G by order of N of A equals index of the N of A in G. That equals the number of distinct right cosets of N of A in G. Okay, by using the Lagrange's theorem, we using that word meaning cosets. Okay, right. To prove the theorem, it is enough to prove that there is 1-to-1 correspondence between conjugate of A and right cosets of N of A in G. That is 1-to-1 correspondence. That means which condition satisfying by conjugate, that condition is satisfying by right cosets. Which condition satisfying right cosets, that same condition satisfying conjugate. That is meaning 1-to-1 correspondence. Okay. For this, we first, so that two elements in the same right cosets of N of A in G corresponds to the same conjugate of A. And two elements in different right cosets of N of A in G give rise to different conjugates of A. Okay, right. Suppose XY belongs to G or in the same right cosets of N of A in G. Therefore, N of A X equals N of A Y. This implies XY inverse belongs to N of A. Since H A equals HB, this implies AB inverse belongs to HB using this. Okay. This implies XY inverse A equals A into XY inverse because normalizer. This implies both sides we multiplying X inverse XY inverse A equals X inverse A XY inverse. This implies Y inverse A, that equals X inverse A XY inverse. We using associative law. So we change the bracket. Okay, this implies next we multiplying both sides Y inverse AY equals X inverse AX, Y inverse Y. This implies Y inverse AY equals X inverse AX. Okay. So, XY belongs to the same conjugate of A. The two elements we take from right cosets of N of A. Now we get that elements equals in same conjugate of A. Okay. Suppose XY belongs to two different right cosets of N of A in G. Therefore, we have N of AX not equals N of AY. To prove that the conjugate of X and Y are different, different right cosets of n of a. So our claim is that conjugate is different. That is to prove x inverse ax not equals y inverse ay. Suppose we take x inverse ax equals y inverse ay. This implies, same calculation we use that, both sides multiplying x, we get x into x inverse ax y inverse equals x into y inverse ay y inverse. This implies ax y inverse equals x y inverse a. This implies x y inverse belongs to n of a. From that condition we get n of a x equals n of y, which is contradiction to 1. We take n of ax not equals n of y. Now we get n of ax equals n of ay. So therefore x inverse ax not equals y inverse ay. That is, x inverse ax and y inverse ay are different conjugates of a. Therefore, there exists a one-to-one correspondence between the conjugates of a and the right cosets of n of a in G. Okay. Ca equals order of C of A. Order of C of A means that number of elements conjugate to A. Number of elements conjugate to A equals number of right cosets of n of A in G. Number of right cosets of n of A means index of n of A in G. Index of n of A in G, that means that equals order of G by order of n of A. Therefore, Ca equals order of G by order of n of A. Thank you.